In this example, we are using vectors in mechanics. We have a particle of mass half a kilogram. It's acted on by three forces. Part A, find the resultant force, capital R, acting on the particle. The thing we need to know here is vectors make finding resultant forces much easier. So the resultant force in this case R is simply the sum of the vectors acting. So F1, F2 and F3. Add them together. Simple as that. F1 plus F2 plus F3. Don't make any silly mistakes. And there's our answer. In part B, find the acceleration of the particle, given your answer in IJK notation. So we've got force, we've got the resultant force, we know the mass of the particle, and we're trying to find the acceleration. So that must be Newton's second law. Please note here that F and A are both vectors, but M isn't. M is a scalar, M for mass. So these are both vectors. If we rearrange F equals ma to get the acceleration, simple numbers again, using your answer to part A, we're dividing by the mass, and make sure you remember to give your answer in the IJK notation with units as well, meters per second per second. Part C, find the magnitude of the acceleration. Simply find how large this vector is. So that's 3D Pythagoras. Be careful when you're squaring the -2 and the -6. And in part D, given that the particle starts at rest, find the distance travelled by the particle in the first 6 seconds of its motion. Well, we know the acceleration. We found it in part B. And it is constant. It's not going to change over time. We see there's no variables here. There's no variables. That makes it a constant. So because acceleration is constant, we can use a Suvat equation. Also, important to note that the particle will not change direction during this motion. We need to be careful of that, because if it started somewhere, travelled forwards, stopped, turned round, and started coming the other way during these 6 seconds, then we'd have to be a bit more careful and break it up into 2 chunks. We'd have to work out how far does it travel forwards, how far does it travel backwards, and add them together if we want the distance. If we just wanted the displacement, then that wouldn't matter so much. But the good news in this example is it does not change direction, so we can just go ahead with a straightforward Suvat. Here it is. We know A, we know U, the initial velocity, we know the time for the journey, and we want to find S. Now I've used the magnitude of the acceleration because the question wanted a scalar rather than a vector. Distance is not a vector, it is a scalar. So for that reason, I used the scalar version of the acceleration. Alternatively, I could have used the vector version of the acceleration here, and then at the very end, I would have had to have found the magnitude of that vector because the question wanted distance rather than displacement.